Okay, so two common logs. Well, two special logs. First of all is the common log. It's common because we use it all the time. We write that as y is equal to the log of x. It's so common that we don't even put a base. We get lazy and just don't write it. But the base here is 10. And so it's a common log because we work in a base 10 system. So when you do not see a base, we're referring to base 10. And exponentially, we could write this as x is equal to 10 to the y. So 10 to the y is equal to x. Another one's the natural log, and this occurs in nature and in many different applications. So we usually write that as y is equal to ln. It's read the natural log of x. And we understand here that the base is e, that number that we came up with last time. And so the exponential form of this is x is equal to e to the y. So e to the y is equal to x. All right. So let's do some evaluating with these. So if I ask you about the log of 100, that would be equal to 2. Why is that? Okay. Remember, we're in base 10. So if I wrote this exponentially, what I'd say is 10 squared equals 100. And that's true. We could think about the log of 1 over 1,000. And what should this be equal to? Well, our base is 10. So 10 to some power, that's what we're looking for here, must be equal to 1 over 1,000. Okay, so 10 to some power equals that. Well, okay, let's try and write this as in base 10. So this is 1 over 10 cubed. And then using our rules of exponents, I could bring this up and make this 10 now not to the positive 3, but to the negative 3. So 10 to the negative 3 is equal to is equal to 1 over 1,000. Let's work with the natural log. Okay, so if we have the natural log of 1, what should this be equal to? Okay. So remember, the base here is e, and we're going to take e and raise it to some power, and when I'm done, that should be equal to 1. So I don't know, e to what power equals 1? Well, the only thing that could possibly be is e to the 0 power, because anything to the 0 power is 1. We could also talk about the natural log of e itself, and what should that be? So again, we're asking about, this is the base e, so e to what power will equal itself? Well, it must be e to the first power is equal to e. I hope these make sense. Give them a little bit of thought, and thinking about moving in between exponential and logarithmic form. So let's use some of this to solve equations using logarithms. Here's a property that we should realize. Okay. So if I take the log of any base of some argument, let's call it x1, and I set that equal to the log of the same base of a different argument, then what we can say is that x1 has to equal x2. It's the same reasoning as this. If I gave you an equation that said x over 3 is equal to 2 over 3, and then asked you what x had to equal, well, since the denominator is the same, the numerators must be the same, so x must equal 2. So the idea is the same here. If I have the log of the same base of two different things, but they're equal, then those things must be equal as well. So for example, if we had the log base 2 of x was equal to the log base 2 of 8, something like this, then these bases are equal, so it must be that x equals 8. Just has to be. Here's another example like that. Say, for example, we had the natural log of x squared is equal to the natural log of 7x. Okay. Now, these are the logarithm of the same base, so it has to be, since these two are equal, that x squared must equal 7x. So let's subtract 7x over to the other side, equals 0. Then I can factor this, so x times x minus 7 equals 0. Now it's factored, so it's either that x equals 0 or x minus 7 equals 0, so that x equals 7. So we have two possibilities here. We have that x equals 0 or x equals 7. But let's check. Okay. Remembering that the natural log, like any other log, looks like so, a basic. Okay. This has a y-intercept of 1, 0, has a vertical asymptote at x equals 0. So, using this and this graph, do we keep both of these? X equals 7 is out here, and certainly we could have a point up here on the graph, 7 comma the natural log of 7. That would certainly exist. However, if I try and put x equals 0 into the natural log, I find that that lies in the horizontal asymptote, vertical, asymptote, and so this is actually an extraneous solution. This is not in the domain. So it turns out we really only have one solution where x is equal to 7. We could also solve some equations like so, by writing them exponentially. So for example, if we have the log base 4 of x is equal to negative 3. Well, I don't know, but I could write exponentially. So I know that 4 to the negative 3 power would have to be x, because this is the exponential form. And then I could just manipulate this. Well, 4 to the negative 3 is 1 over 4 cubed. 4 cubed is 16 times 4, which is 64. So x would be equal to 1 over 64. And we could do our check. Okay. So the log base 4 of 1 over 64 is equal to negative 3. And it works. 4 to the negative 3 is equal to 1 over 64. It might be interesting to note here as well that 1 over 64 was the same thing as 4 to the negative 3, and we saw that was equal to negative 3. And we'll see this happen later. When this base and this base agree, the answer will become the exponent. We could have something like 5 to the x is equal to 9. The problem here now is that we need to get to the variable, and the variable's in the exponent. Okay? So in this case, it is an exponential form, but we need to get to that exponent, so we need log form. Okay? So if I write this logarithmically, I will have then that x is equal to the log base 5 of 9. Okay. Now this is an irrational answer, but this is the exact form of the solution. So I think that should get you through your homework. Yeah, just understanding what the log graph is and how to shift it around and some basic solving properties about it before we move on from here. All right, email me if you have a question.